Okay, good morning everybody. Today we start with our last chapter, our last unit, chapter 16 from the book, and we will discuss radioactivity, we will discuss fundamental particles, characteristics of radioactivity, and so on things. Okay, let's start at the beginning and talk about the atom. Now, let's first talk a little bit about the history of the atom and how are the atom structures and how did they get to come to their ideas. Okay, Democritus was the first one who actually gave a small description about the atoms. He said, nothing exists except atoms and empty space. Everything else is an opinion. And atoms can have different types of shapes, right? Then we move on to the 19th century to John Dalton. He made actually already some models about atoms and how they interact. Yeah. First of all, he described that the atoms are very, very small particles. All the atoms of a given element are identical in size, mass, and other properties. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements can combine in simple whole numbers ratio to form chemical compounds. And in chemical reactions, atoms are combined, separated, or rearranged. So his ideas have gone already pretty far in describing how atoms could interact. Okay. In our next model, we are going to talk about Thomson's plum pudding model. He actually discovered the electron using a beam, and we're not going to describe the experiment. However, it's like a tube, a gas is heated up and electrons are released. And how did he know that these particles were electrons, or he called them electrons, if he put an external field or a magnet along the tube? He saw like it was bending, maybe something that you have heard already when we were talking about the electric field. So he described his model as plum pudding because it looked very similar to a plum pudding. So in the description, he described the atoms have electrons, called negative charge, and somewhere around there must be some positive particles. Okay? They didn't know anything about the nucleus yet. In the next discovery, which was very important, we discussed Ernest Rutherford's experiment. Do you remember which important experiment he did? You should know a little bit about from the RGCSE physics or chemistry. Okay? And what did he conclude from his analysis and observation? Now let's first look at his experiment. And it took him a while to figure it out. But the experiment looks more or less like that, and you might have heard about the gold foil experiment. Okay, so he had a radioactive source which was beaming out alpha particles. At that moment, they knew already that the alpha particles were positively charged. Yeah, alpha particles. And he directed them to a gold foil, very, very thin. Later we will discuss why he actually chose a gold foil and no other material. In the back, he had like a kind of a detector that actually could detect if an alpha particle would hit the screen. Now, very interesting already, and you might know already about this experiment. He saw actually that most of the alpha particles went straight through the gold foil. Another conclusion, or well, not conclusion, but he saw actually only a very few alpha particles were scattered. Or they were scattered in different directions, or they even were bouncing back. Okay? Now, as usual, if you want to make notes, just pause the video and make some notes, and then just continue with the video. Okay? Right. Let's look at his results. He was expecting that the alpha particle would just pass through the plum pudding model. That was the only model that they knew at that moment, and would leave the gold atom undisturbed. So, what he was expecting is alpha particles just go straight through the plum pudding model. However, actually what happened is that 99%, I do not know exactly the percentage, just went straight through the gold atoms. Yeah? Only a very small portion of the alpha particles were deflecting, meaning because of the deflection, he concluded there must be somewhere in the atom a very tiny positive charge, somewhere. And they called it the nucleus. Now we know that the nucleus contains protons and neutrons. Yeah? Now, alpha particles have a positive charge, so when a positive charge comes close to the nucleus, it will be deflected or even bouncing back. Okay? Okay, now let's look at the output, the Rutherford experiment. If it's good, I have this already. I have to go out. And then we go to the Thomson, the Rutherford scattering model. Let's look first at the plum pudding. This was what he expected, because they only had the knowledge of the plum pudding, and that all the alpha particles will actually go through the model. Okay? Now let's look at the Rutherford's experiment. I hope you can see it. We have alpha particles, and when we look at it closer, we see that I want to have a constant stream. Let's increase the amount of atoms, protons. You can do this experiment, you can look at this experiment or this applet yourself. You go to Flat, Colorado, and you find this one. Now let's look. Now if we look closely, we see the particles that come very close. They are being scattered. or even bouncing away. Okay? Let's go back to the PowerPoint. Okay, let's have a small look at that effect. You have to consider if a particle is moving, and we have like a hi-hat in the middle, and this is representing actually, and you can look at the pictures in your book, yeah? We have the particles, alpha particles, and when they enter, and this represents the nucleus, okay? They like go, not like that, but like go in different directions when they are close, or even going back, okay? So that you have an idea that the nucleus, remember, positive particles, and the alpha particle is positive, okay? All right. Okay, some notes about the experiment. And you need to know some characteristics of this experiment and make some notes about it, okay? First of all, alpha particles was encased in a metal so that we only had a small beam of particles to emerge. Otherwise, it would have been we would not get a real good experiment. You really have to like a beam, small beam, entering the gold foil. Air pump. Air in the apparatus was pumped out to leave a vacuum because alpha particles are absorbed by about a couple of centimeters air, so you don't want that, okay? The reason for gold, simply, as you know, that metals are very malleable, and especially gold, and it can be made in very, very, very tiny sheets in about hundreds of atoms thick, and I can tell you that is very, very thin. Yeah. Alpha particles were detected on a scintillating material. What does it mean? When the alpha particle hits the scintillating material, it gives a tiny flash. Yeah. So the detector is actually constantly moved away in order to see if there was any particle that was deflected. Now you must think about this and we go back to the experiment, to the picture. You must think that you only have one detector here, and every time they moved it, and they moved it, and they moved it, and they moved it, and they just checked if at a certain moment there would be an alpha particle that would be deflected, and then here would give a flash on the scintillating material. So you can imagine that this experiment took weeks and weeks before they even detected a particle that didn't go straight through, okay? Yeah, so the detector could be moved around to detect the alpha particles that were scattered, okay? All right, So now we have a model. We knew that we had electrons. So this is our atomic model. We knew that we had a nucleus containing positive particles, which of now we know that these are protons, and we had electrons, yeah, because simply they could detect whether an atom had a charge or not. No, atoms don't have a charge because they have equal amounts of protons and electrons. Okay? Now let's look at a simple atom. And could you draw a diagram of the lithium? Now, and the parts. Now, where do we find lithium? Lithium we find as the third atomic number in the periodic table. When we know it has the third atomic number, that means it has 3 protons. When we know it has 3 protons, we also know it has 3 electrons. Okay? Later on, they developed models about how electrons behaved around the nucleus. Yeah, chemistry students, you must know about electron shells or even orbitals, as orbitals, etc. Okay, so we have the proton, 3 in this case, and we have 3 electrons, meaning it's neutral, and later they discovered also the neutrons, yeah, which we'll talk about later. So, 3 protons, 3 electrons, 4 neutrons in this case, and the protons and the neutrons are found in the nucleus. We call them the, don't forget that name, the nucleons, and the electrons are found in shells orbiting the nucleus. That's all they more or less knew. Later on, you know that they are actually in orbitals. Okay? All right. Not so important, but here's a picture of atoms in a crystal. Yeah. Very, very, very tiny, and many atoms are actually arranged in a crystal, especially the metals. Okay? All right. Just make a note. If you want to, just stop the video, make some notes, and then just continue the video, okay? Okay. Now we're going to look what is the charge and mass in SI units, the relative units for the proton, neutrons, and electrons. We're going to define specific charge and calculate its value for nuclei and ions. I'm not going to deep into that. And we interpret the nucleate notation, including the proton number and the nucleon number. Okay? Right. And we define what is meant by an isotope, but you know that already. Okay? Some important facts to understand is that the nucleus is super small compared to the atom. It's about 10,000 times smaller. If this would be the size of the atom, and then I would point out the size of the nucleus, it would be like this big. Like this, hardly to see. Yeah, very, very, very small. Okay. diameter of the atom is in the order of 10 to the negative 10 meters, and whereas the diameter of the nucleus is in the order of 10 to the negative 15 meters, or femtometers. Okay? The atom is a very dynamic entity. The diagram that we use shows a stylized representation, but of course the reality is that there is a complete disorder at atomic level. Okay? Alright. Let's look inside in the atom and we look at the properties. Okay? Then we look at the charge. The charge of electrons -1, it's the standard charge of an electron. The proton has a positive charge and they are equal to each other. Neutrons, they don't have a charge. If we look at the masses, and actually you will see why we actually say that the mass of the electron is negligible. If we compare it with a proton and neutron, we see 9.1 times 10 to the negative -3. Proton 1.67 times 10 to the negative 27, and the neutron 1.67 times 10 to the negative 27. So we see that the relative mass of the electron is very small, and when we are calculating the atomic mass, we mainly calculate actually the mass of the amount of neutrons and protons together. Okay? Alright. Know that the unit charge of one electron is 1.6 times 10 to the negative 19 coulomb. Okay? So both of them, one electron equals to the amount of charge of the proton. So in an atom we always see that the amount of protons are equal to the amount of electrons. Okay? Yeah. And a neutron has no charge but has the same mass as the proton. Right? Okay, let's have a little bit a look at the radius, and you need to know these numbers. Okay, as said before, the radius of an atom is about 10 to the negative 10 meters. The radius of the protons is 0.8 times 10 to the negative 15 to 0.87 times 10 to the negative 15 meters, or femtometers, and the radius of the neutrons is more or less the same as the protons. So we may say more or less the volume of the protons are equal to the volumes of the neutrons. When we look at the atom, and we see that the atom has a range from molecular atom has a range from 10 to the negative 10 to 10 to the negative 6. Now, it's interesting to know where does all this mass come from in an atom. That is, of course, from the nucleus. Okay? Now, we have said already that atom is virtually empty, especially when we are considering only the mass of an atom. So we could calculate actually the density of an atom, which we come to that later. A quick quiz. We saw already the lithium atom. Just go back in the video. Lithium has 3 protons, 4 neutrons. As it has 3 protons, it also has 3 electrons. If we look at carbon, carbon has 6 protons, 6 neutrons. How could you draw out a carbon atom in a similar way to the lithium atom? The diagram, well, I can put it here. We have 6 protons, 1, 2, 3, 4, 5, 6. 6 neutrons, I'll just put them here. 6. Then we have 6 electrons. For the chemistry guys, we know that we have the first 2 electrons in the first shell, and then when we look further, we know that we have the other 4 electrons in the second shell, so we have 6 electrons first shell and second shell. Okay? How can we find the total charge of the carbon nucleus? That is actually 6 times plus E. You could calculate it alone, because that is 1.6 times 10 to the negative 19, so we get 6 times 1.6 times 10 to the negative 19. This is only for the nucleus. For this one, protons is positive. If we would do the same, 6 times for the electrons, minus negative, so that is 6 times 1.6 times 10 to the negative 19 negative. And they are equal to the charge of the protons. Okay? Right. Now it's interesting to know how we can calculate the density of the nucleus. And you can look in your book. Now, we know already what is the mass of a proton. We know what is the radius of a proton. We might say we can calculate then, the volume of a proton. We might say that actually a proton is a sphere. We can calculate then 4 pi r squared when we calculate the volume of a sphere. And then we find here the volume. If we want to calculate the density, well, density is mass over volume. The mass of one proton is 1.6 times 10 to the negative 27. We divide it by the volume, and we get here the density for a proton. Now, how do we get the density of the nucleus? It's pretty simple, because neutrons have roughly the same density. Yeah, so the density of the atom is roughly 10 to the power of 18 kilograms. 10 to the power of 18 kilograms per cubic meter. That's interesting, no? If we compare the density of water, that's 100 kilograms per cubic meter. So, if we would take away the volume of the atom and only would consider the volume of the nucleus, and I would fill this beaker, I think I have more or less the same mass as the Earth. So you can imagine. Yeah, these are calculations that you are supposed to do. It's pretty simple. When the radius of the proton is given, the mass of the proton is given, you can calculate the volume of a proton because we consider it as a sphere, and you can calculate easily the density. Okay? All right. Let's define the isotope. Isotopes are atoms with same number of protons, but they can contain different amounts of neutrons. Okay? So different elements can have different amounts of protons. Okay? Now, how do we notate a isotope? An isotope, sorry. Yeah? Well, we distinguish by the different numbers of protons and neutrons, and we discussed already nucleons and proton number. Okay. Now, don't forget, on the top we put the atomic number, nucleon number, sorry, and in the bottom we put the atomic number or proton number. So this number defines the amount of proton, a nucleon number is the amount of protons plus neutrons. Okay? So the nucleon number is actually the mass number of an atom. X represents the chemical symbol. Okay? Now, when we have a different isotope of the same element, it means that only the mass changes. Okay? Interesting. What will happen if the proton number is going to change? Well, if we change the proton number, we get a completely different element. Yeah? Okay. As said, isotope notation, we can calculate the amount of neutrons by doing nucleon number minus proton number. Now, when we are talking about an isotope, no charge, overall charge, it means it has the same amounts of electrons. Okay? So, isotopes, same amount of proton, different numbers of neutrons. Yeah? Isotopes don't have different chemical properties. Okay? Chemical properties depend on which element we are talking about. Okay? If proton number is changed, then the element changes. Okay? Some isotopes can be unstable and they are radioactive. Okay? Some examples of pretty important isotopes, and you might have heard about it when we look at a normal hydrogen atom, which occurs most of the time. We call it protium, which is hydrogen. And remember, hydrogen only contains a proton and an electron, does not contain a neutron. When we talk about deuterium, it has one neutron, one proton, and you see 2 and 1 here. And when we talk about tritium, it has 3 nucleons inside the atom, 2 neutrons and 1 proton. Other elements, neon, and we see neon can have also different amounts of protons. Okay? Alright. In your book, you see a list of some other isotopes. Yeah? And for the chemistry students, you did already. How do you have to find the average atomic mass? Well, you have to add up the mass percentages of all the isotopes, and then you can find the average atomic mass. Okay? So when you look at the periodic table, these are not whole numbers, you will see different numbers, okay? Because they have different isotopes, okay? We're not going to do this, but you can do that for yourself. You could actually find the charge, the mass, and is it an ion, of which element you can find that. Yeah, we're not going too deep into this, okay? All right, don't forget that For chemistry, actually we are only interested in the electrons in the outer shell. Okay? Nuclei do not involve in any way and remain totally unaltered even in the fiercest of chemical reactions. Okay? How many protons? How many neutrons? We know that carbon has the proton number 6, so the amount of neutrons is then A minus C is 8. An amount of electrons is the same as the amount of protons, so should be the same. Okay? Okay, so carbon 14 is an unstable element, yeah? And it could decay so that one of the neutrons turns into a proton. What's going to happen? Yeah, the amount of protons goes from 8 to 7, and the amount of the amount of neutrons. Well, let's write the element and see what happens. So we have 14, 6 is the amount of protons, and neutrons, 5, 8. Now one neutron is going to become a proton. Now what's going to happen? Is the total mass going to change? No, it stays the same. However, we get now an extra proton, becomes 7. Something wrong here? Yes, something wrong, because when the proton is going to change, it means the element is going to change, and it will then be nitrogen. Okay? Now, finishing this up, don't forget, the nucleus is the massive positive charge center of the atom. Neutron is an uncharged particle found in the nuclei of most atoms. Nucleon are protons or neutron in the nucleus, yeah, so proton or neutron, and the nuclei, different types of nucleus of the same element with different numbers of nucleons. Okay? In summary, all atoms are made of a nucleus with orbiting electrons. The nucleus is made up of protons and neutrons, nucleons. Isotopes have the same numbers of protons, but numbers of different numbers. Isotopes represented by AZ, where A is the nucleon number and Z is the proton number, and we can find the number of neutrons by doing A minus Z. Nucleus is positive, yeah, charge, and very small. Okay? Now make notes, and I will upload very soon next video.